review of this experimental form of physics tutorial. I've started off in this technique, slowed up, got a few feedbacks about volumes and presentation, then got off exploring podcasting, how to go through synthetic lessons, and indeed it is complex in terms of there's a lot of ideas to get across, and there's a lot of poorly, well, I just can't quite frankly say that they are poorly thought out or thought through or thoroughly thought through. They're correct within the frame of reference. I should say that frame of reference of the school, but in general physics, they're not necessarily up to scratch, so you have people asking questions, normal questions they don't understand, but their response or understanding is actually significant because they've actually understood better than perhaps the people teaching them. And it's question 2 of the multiple choice of the 2017 exam, HSC physics exam. And the question reads as follows: which of the following is an inertial frame of reference? So reading back, a frame of reference, what is that? What is inertial? And then which of the following is that inertial frame of reference? So that's the way we're going to go. We're going to look at frames of reference, what's inertial, then go through it. The options that you're given, and I think you should note this, that the questions are given with extended length. So that's how they're ordered. So you don't get clued as to what's right or wrong. It's either that or something else. Now, the first is a rocket during launch. And obviously, that's an accelerating frame. A train travelling at a constant velocity. A constant velocity means its velocity isn't changing, it's not accelerating. A car turning a corner at a constant speed, its velocity is moving, its acceleration. So if you're travelling that way, the acceleration is at 90 degrees to velocity. A lift slowing down as it approaches the ground floor. Now, as we'll see, this is almost qualifies to an inertial frame of reference or a limited inertial frame of reference, as in. Now, as said, rather than going into the options straight away, we'll go into the question and work backwards all the time. So let's read this. In physics, a frame of reference or reference frames consists of an abstract coordinate system. So it's actually a concept. You can't actually have a coordinate. We used to joke at school we had the coordinate system was held in Paris. And a set of physical reference points that uniquely fix, locate and orient the coordinate system and standardize the measurement. So there's usually a unit meter in various directions. So you've got a unit x meter, y meter, z meter. So normally, and one of the important things is you've got a frame of reference. The frame of reference has a descriptor. It can be the x frame of reference, the 10th frame of reference, or someone's frame of reference. And the frame of reference in general refers to a person. You know, Peter is frame of reference. My z-axis is that direction. My x-axis is that direction. Y-axis is that direction. In general, it's like that. Now, if I turn my head, the axis changes. In general, conceptually, it's an axis system from your head or from the room that you're sitting in or something like that if you're moving about, or in the car. So it refers to the reference system of the car. It would then mean that would be defined by the wheels of the car, direction of the car moving. So the z-axis of the car will be where you're going forward, and the four wheels will determine the x-axis and the y-axis. Now let's read a few of these comments here. 2 stupid chickens. How do I get to the other side? You are on the other side. That is not being able to comprehend that someone else has a frame of reference. And here Susie prefers to carry her own frame of reference, which is essentially what you do when you carry a frame of reference. And that's the important thing when we say the frame of reference of the rocket, of this thing, is the next thing is what is an inertial frame of reference? And we'll read the actual strict definitions here, and then we'll start to unpick that a bit more to get into the school definitions where it's a bit woolly. Now, the inertial frame of reference, the systems in which Newton's first law of motion holds good are called inertial frames of reference. That's a strict definition. Newton's first law is that something at rest or travelling at a constant velocity, or a constant speed or direction, will remain at rest or at a constant speed or direction regardless, unless an external force is acting on it. So they're saying there's no external force and there's that. Now, of course, in the train, if you were to drop, let a ball down, it would drop vertically down. So it's a limited frame of reference. A non-inertial frame of reference. So that's pretty much on the Earth, because the Earth is spinning. The Earth's rotating and spinning, the Coriolis force. Systems in which Newton's first law of motion does not hold good are called non-inertial frames of reference. So if I have an object and it's sitting in front of me and it mysteriously begins to drift, there's some force which goes like that. Or like if I hold something up and it just drops down. So that's non-inertial frame of reference. A frame of reference which is accelerated motion with respect to inertial frame is called a non-inertial frame of reference. So let's look at this. So I've got over here, up the top here, in this area here, an inertial frame of reference. I don't know what the ROCV, rest or constant velocity. That's what ROCV, rest or constant velocity in no gravitational field. So it's rest and constant velocity, and there's nothing accelerating. So you're in absolute deep space, completely deepest space actually outside the universe, if possible, a long way from any source of gravity. Your object, if it's placed, will just sit there, and if you give it a push, it will travel forever onwards. Now, this is, you might say, well, that might exist in the space shuttle. Well, what actually happens is that if you put two balls on top of each other in the space shuttle, you're traveling in the space lab, what will happen is that the actual balls will actually begin to drift apart. They'll be because the ball at the top will be travelling too fast for its position, and this will be travelling too slow. There'll be a tidal force that will come across. So even though the space shuttle is often touted as providing an inertial frame of reference, it's not quite. There's a slight gravitational pull. You need to be objects in free fall in a parallel gravitational field. Here the gravitational field's got a slight angle to it, and so you're going in a circle around a point, and it's going across. So in the vomit comet, this is the plane which goes up and down, and on the top, it's your frame of reference as measured by you. It appears that Newton's first law applies in all three dimensions, and so this is a contrived thing. You could actually build something with a linear gravitational field and have it in free fall, but the gravitational field always tends to point towards the centre of the Earth. That's the way that we are built at the moment. Now, there's this thing which is not in the literature, not defined in the textbooks very well, and that's called the limited frame of reference. And the best way of thinking it is a billiards table. It is accelerating down, but you have a normal force which cancels out that acceleration, so your eyes are not distracted by the fact that it is accelerating. And then this is in the y direction. As far as we're concerned, the x and z direction are free to rotate. So this is also inside the train. It's called a limited inertial frame. So really the question to say which of these are non-inertial frames or now a rocket during launch. Now I've shown the rocket frame of references at several points, I think 5 seconds apart, and you can see that it's travelling at a non-uniform velocity, and you'd be able to see things not go off. And the interesting thing is that it would be you might be saying, look, I'm sitting still, I'm in an inertial frame of reference, and you drop something, it drops down. It's also the rocket is experiencing stronger gravitational field. Again, it's just because of the textbooks. It's obviously accelerating. So they're looking at the word, it can't be accelerating. Well, it is accelerating, but someone sitting down is also complicated to go across. This is the dial, a train travelling at a constant velocity. Yes, the velocity means it's not changed direction, but it assumes it's not on a slope. So yeah, if you are travelling at constant velocity but up a hill, your frame of reference therefore has a gravitational component in it which you can't cancel, and so you would see, say you're at constant velocity travelling up a hill, your ball you put at rest would start to accelerate towards you. Just that's the way it is. Maybe it's technically a two-axis limited frame of reference. So theoretically, if I sort of drop this, if I had this in my train, Newton's first law, just watch Newton's first law of gravitation, that's Newton's first law, but if I let it go, it's the next one. Whoops. Come on. See if I can go back. You saw there the car just went through. I wish I could do it. So I've got these really daft keys. The car is obviously turned around. The lift slowing down as it approaches the ground floor. Now, again, you could be a limited frame of reference. That is, play billiards in your lift, and you go up and down, and you wouldn't see any effect on your billiards playing. And so it would be inertial in that plane, but not inertial in this frame. And it's never inertial. There's always accelerating some way. Now here's the next question, and I've decided to write and build it up so you can see it. Which of the following correctly shows the electric field between two parallel charged plates? And the charges are shown there. And let's go through some of the conventions with electric fields and how they're drawn, because they don't necessarily follow them as well as one would like. So electric field lines emerge, each electric field lines emerge from a positive or a group of positive charges and finish on a single or a similar sized group of negative charges. So that's a field line. So now a field line is the invention of Michael Faraday, and it is a conceptual marking. It's actually not a physical object. So an electric field, I can't gather up so much electric field and sell it to you. I can sell you so many atoms, I can sell you so much charge. I can't sell you field lines. Field lines, very definitely a concept. And we go across here, they start on positive charges and end in negative charges. And just with that simple piece of information, we can see that A, which is this one up here, A is the correct answer. Well, but how correct is it? Well, the interesting thing in physics, the charges that we draw go to the surface. If that's a metal, that could be charge. In general, we call it a charge plate. And charges and metals always go to the surface because they're free to flow. So in general, so you can see over here on the surface here. Now, what we have here is a field vector. Here, you see this field vector? It's like that. It's an arrow in a direction. So it's that length. It can be the length. It's three vectors. The thing is, I can pick that vector up and add it by vector addition around the place. That's a vector. It's E equals sigma, the total charge on the permittivity of free space, which is the number of farad, which is capacitance per meter. There you go, and it's that number there. That is actually a property of our universe. It's a property of any space. So if I get a chunk of our universe, a square meter, from anywhere, it will have this. So it will also have a magnetic value, and the two values together define the elasticity, electromagnetic elasticity, and the speed of light through. But one of the points here I want to say is here, this is correct of placing charges. So you have the charges here placed up against the wall here. So really, technically speaking, we want the charges like this. Okay, and now here's another thing is that you'll note here that correctly drawn, the field lines are a force line, and really, technically, they should be like this. Those are not, although many diagrams and many books have it incorrect, having it like that is incorrect. I wonder if I can actually scrub this out. No, come on. Oh, that's all I have to do, yeah. No, it won't let me. I would scrub the arrows up. So technically, field lines should be there. Now, even more technically, this is a proper plate because the field lines, there's side, they're called parasitic or edge effect field lines, which continue all the way around. There's even some field lines coming out of the back of the plate here. But it is important that they do start and terminate at a charge here. So it is right, but it's really interesting that you subtly teach people incorrect methodologies. So when you later come along and you say, a student gets a very poor mark, and it's got a good way of doing things, or a student gets a very high mark and they're no longer receptive. It's like it's a lose-lose situation, making these small little errors make it actually quite hard to actually pick up the game and move it forward. That's just my opinion. Thanks for watching.